Welcome back, focused learners. Let's jump right into today's explainer. If you've ever wondered how we take a totally abstract human idea and systematically transform it into a running, breathing computer program, you are in exactly the right place. Today, we're tearing down the programming phase, sometimes called the implementation phase. We're going to see exactly how a logical algorithm gets turned into a flawless, executing piece of software.
To get there, we've got a clear 5-step assembly line to walk through. We're going to start by laying the groundwork with coding and packs, climb up through the different levels of languages, grind our way through compiling and debugging, actually run and test the thing, and finally, lock it all down with documentation and maintenance. It's quite the journey, so let's get right to it.
All right, stage 1. Before a programmer even thinks about typing out actual code, they have to map out the logic. It's kind of like drawing up a blueprint before building a house. They do this by translating their solution steps into flowcharts, algorithms, or what we specifically call a problem analysis chart, or a PAC for short.
Okay, let's dive into this with a really practical example. Take a look at this PAC for converting miles to kilometers. Notice how incredibly structured this is? We always have a distinct start and an end. Right in the middle, we have read miles, that's our raw input. Then we process that data with our formula, kilometers equals 1.609 times miles. And finally, we print kilometers, giving us our output. It's a completely precise, step-by-step trace right from input to output.
Let's reinforce that concept real quick with another one, calculating the area of a circle. Again, we read the radius. We apply the raw mathematical rule, right? Area equals 3.14 times radius. Then we print the area, and we end. This is a perfect illustration of how raw math gets translated into a highly structured PAC way before any real coding actually begins.
So, once our logic is all laid out nicely, we enter the coding phase. This is where we actually translate our algorithm into a language the computer can understand. But, that brings us to a really massive shift in our assembly line, the actual levels of the languages we use.
Which begs a pretty fascinating question, doesn't it? How do computers actually understand our instructions? Because let's be honest, there is a massive gap between our human ideas, like those math formulas we just looked at, and the physical, electrical actions a machine takes.
Well, to bridge that gap, programmers use different levels of languages. And definitely note this carefully, especially for your exam prep. Languages are broken down into low-level and high-level categories. Machine language and assembly language, those are low-level. They are hardware-dependent, meaning you literally have to know the specific computer hardware inside and out to use them. Procedure-oriented languages, on the other hand, are high-level, and they are machine-independent. You can run them on any hardware. So let's climb this ladder, starting at the absolute bottom.
Now, what's really interesting here is this string of numbers: 16, 128, 64, and 8. This right here is machine language. It strictly uses numbers to represent letters, alphabets, or special characters. In this specific payroll example we're looking at, 16 is actually an instruction code telling the computer to add. The numbers 128 and 64 are the specific memory addresses where regular pay and overtime pay are physically stored. And that 8, that represents the storage location where the final total pay will be kept.
But wait, it actually gets even more fundamental than that. Sometimes these are represented as pure bit patterns, like 10000, 100000, and so on. Now, while this binary representation is absolutely ideal for the computer's hardware to process in a fraction of a millisecond, imagine being a programmer having to write a massive program this way. There is just no way. You'd go cross-eyed in about 5 minutes. It would be incredibly difficult and just hopelessly tedious.
And honestly, that exact tediousness led to the second tier, symbolic or assembly language. Instead of raw bit patterns, it uses fewer symbols, letters, and special characters. So our previous string of numbers becomes add lock 1, lock 2, lock 3. This simply means add the contents of location 1 to location 2 and put the resulting total in location 3. Now, it's still closely related to machine language. One symbolic instruction still translates to exactly one machine instruction, but man, it's so much easier for a human to read.
Finally, we reach the top of the ladder, procedure-oriented languages. These are our high-level, machine-independent languages. Think C, C++, Pascal, COBOL, BASIC. But here is the crucial rule your instructor wants you to remember. Because these are high-level, the computer hardware literally cannot understand them directly.
they absolutely must be paired with a special program called a compiler. That compiler's job is to translate them back down into that raw machine language.
And this brilliantly illustrates the whole evolution. Just look at how the exact same payroll edition changes its syntax across the different language levels. We go from the raw, abstract numbers of machine language to the abbreviations of assembly, right on up to the highly readable, almost English-like formats of FORTRAN, COBOL, and Pascal. The underlying logic remains exactly the same, but the way we communicate it to the machine completely transforms.
All right, moving right along the stage 3. So what actually happens once we've written all this beautiful, high-level source code?
Well, we enter a very cyclical, highly interdependent relationship. Compiling is the process where the compiler attempts to translate your high-level source code into executable machine form. But, and it's a big but, if any part of your code doesn't follow the exact format or language rules, the compiler hits the brakes and flags it as a syntax error, a bug. Debugging is simply what the programmer does to correct those flagged errors. Then you recompile, and you repeat this sometimes agonizing loop, compile, debug, until the source code is 100% error-free. Which brings us nicely to stage 4. Once we finally have that error-free, executable program in our hands, it is time to run and test the thing to verify it actually produces the intended output.
Now pay very close attention here, because this is a classic exam trap, for sure. You absolutely must understand the difference between syntax errors and logic errors. A syntax error is just a formatting mistake. It's a typo in the language rules that the compiler catches nice and early. But a logic error? Those are sneaky. A logic error happens when your code compiles perfectly, meaning it's completely error-free in terms of syntax, but during testing, it spits out the totally wrong output. Why? Usually it's due to an incorrect sequence of instructions. The computer did exactly what you told it to do, but your underlying logic was flawed from the start. Rigorous testing is how we catch those logic errors. But let's move on to something easier.
And finally, once a program has been heavily tested over a substantial period and consistently produces the right output, we arrive at the very last stage of the assembly line: documentation and maintenance.
The crucial takeaway here is that a program's life cycle definitely does not end when the coding stops. Documentation is absolutely vital. It's required for management use and audits, it's necessary for future software enhancements, and it is a lifesaver when new programmers have to take over operations. Notice that last bullet point on the rules. I want to heavily stress this. Trying to understand the complex logic of a program solely by staring at the raw source code is a terrible approach. You must study the documentation to truly grasp how the whole shebang operates.
Okay, let's do a rapid-fire recap of the programming patterns you absolutely need to remember. The implementation phase has 5 clear stages: code, compile, debug, test, and document. Always remember that problem analysis charts, or PACs, are where you establish your raw algorithm first. When you code in high-level, machine-independent languages, a compiler is non-negotiable. And finally, don't fall for the trap. Compilers catch format syntax errors, but only rigorous testing will catch those sneaky logic errors.
I'm going to leave you with one final provocative thought to ponder. If high-level languages, as incredibly advanced as they are today, still ultimately rely on compilers to translate our human logic back down into raw zeros and ones machine code, what might the next great evolution of programming languages look like? Will we ever truly bypass that machine language barrier? Keep that tension between human logic and machine execution in mind as you continue your studies. Thanks for hanging out with me for this explainer, and keep learning.